change and so on. So it's a pleasure to have you here,
you.
Sarah. And Sarah has a small baby as well, so she can only be here today. It's difficult to be away. Thank you very much.
Right. Thank you very much. Can you hear me if I positioned it correctly? Right, so as Beatrice said, I have this joint post between maths and meteorology, and I'm going to be talking about an applied problem about using meteorological observations. But first, I'll tell you a bit about myself. So I also did my undergraduate maths degree here at Clare College before all these fancy buildings were built. And then I knew that I wanted to do a PhD, but and I had an idea I wanted to do it in fluid dynamics, but I knew I didn't want to stay in Cambridge. So I said to my director of studies, what should I do, where should I go? And he said, well, think about some institutions in America. So I thought, oh, that sounds scary, how can I leave the country? But then I investigated it and I decided I would go for it. I was lucky enough to be offered a fellowship by Brown University in the applied math program there, and I indeed did my thesis on a fluid dynamics problem on sedimentation flows. But then, while I was there, I went on a summer program at the Woods Hole Oceanographic Institution, which is in a beautiful part of the US. It's on the East Coast. It's where lots of presidents go on holiday, and Bill Clinton goes to Martha's Vineyard, just very close by. So this summer program, you go sit on the beach with the blackboard or green board next to you, have a chat with your supervisor for your summer research project. So it was a very relaxed, enjoyable atmosphere, and this influenced me that I wanted to change field from my PhD thesis area to more of an area associated with meteorology. So I wouldn't necessarily recommend that as a career plan, that you do a PhD in one thing and then go and do a postdoc in something else, but I had this experience that made me want to do that. So then I got this postdoc purely in the meteorology department at Reading, and then there was an opportunity to become something called an RCUK academic fellow, which was a special fellowship that allowed you to make the transition between being a postdoc and being a lecturer. So the idea was that you started off doing purely research and then you gradually increased your teaching load to the amount of a full teaching load by the end of the fellowship. So it was the idea was to try and foster a career at the same time as helping you become a lecturer. And that was a joint post between mathematics and meteorology. And as Beatrice says, I am a bit of a go-between between the two departments. We're on different sides of the lake in the university. And I keep petitioning them to try and build me an aerial runway so I can zoom from one to the other. It hasn't quite worked. But, and I've been very lucky there in that I've had some brilliant mentoring on an unofficial basis from a woman colleague who's now in her 70s, but she's still very active, Nancy Nichols, who's really helped me with my career and helped me work out what the best thing to do at what time, and with writing grant applications and learning how to mentor students, PhD students and so on. And there's indeed a picture of my very first PhD student, Gillian, who graduated in 2009. So I have a little boy, Simon, who's just turned 2. He was born on April Fool's Day, 2011, and I took 12 months maternity leave, which is now kind of the default option given under UK law. But I was very lucky in that while I was away on maternity leave, my colleagues, my students and my postdocs were still carrying on working under supervision by my colleagues, and so I was included on various papers and so on, so that when I came back I don't have a gap in my publication record for that year that I've been away. And when I've returned to work, again, the university, partly through the Athena Swan programme and partly because I have people like Beatrice as one of my heads of department, I was given some time off from teaching, or a reduced teaching load for this year, so that I can really focus on getting my research back together, writing grant proposals and so on. And I only work 3 days a week, which is, it can be quite difficult to get everything that I need to do done. But my husband's wonderfully flexible, so I work 3 days a week. My little boy's in nursery for 2.5 days, and my husband actually looks after my little boy for half a day because he works full time but fits it into 4.5 days. So between the two of us, we managed to do drop off and pick up at nursery, for example. I dropped my son off this morning and he's picking him up this evening, so that I can go off and do things like this in order to further my career. So I think that's the way to make it work, is make sure you have a supportive husband. Right, so on to the mathematics of the talk. So what I'm going to be talking about is the numerical weather prediction problem, which is the way we do modern weather forecasting. And in particular, an aspect of that called data assimilation, which is how we create initial conditions for those numerical weather forecasts, and focusing on how we actually use the observations and what the errors in the observations are and how we can model those errors. We model those errors in a covariance matrix called R, and I'll be talking a bit about what some of those errors entail and how we can actually try and approximate what they are in practice, because obviously we're taking an observation of the real world. We have no ground truth to compare with, so we have to kind of make some guesses about what the errors are even. So numerical weather prediction is a solution of a set of coupled partial differential equations, which are essentially fluid mechanics and thermodynamics in complex geometry. So you're trying to solve it on the surface of a sphere, only it's not quite a sphere because you've got hills and valleys and rivers and streams and roads and houses. And the basic flow equations are very well known, but the mechanics that goes on, the dynamics inside a cloud are rather poorly known, what we call microphysics, turning from water vapor, ice, crystals and so on. So we've got a rather complicated system. We treat it like an initial boundary value problem, so we need an initial condition, but we also need forcing at the top of the atmosphere and the Earth's surface. It's also a multi-scale problem, because we're interested in flows happening on global scales, but the turbulent scale, the Kolmogorov microscale, is only a few millimeters for air. So we can't possibly hope to try and model all those scales in one model, so we have to do some approximation. And when we want to do a forecast just for the UK, for example, we do that by nesting a model of the UK in a larger scale model. So in that case, you only model the UK and you have the global model outside, and you get lateral boundary conditions coming in from a larger scale model. And this kind of very high resolution modelling is particularly important for what people call high impact weather, things like storms and floods and intense rainfall, tornadoes, which happen very more often than you think in the UK. So the area that I'm interested in is this area called data assimilation, which is the middle box here, where essentially what we're trying to do is create these initial conditions for the weather forecast. And the way we do that is by blending together observations coming from the atmosphere outside, so that can be things like weather balloons, what we call radiosondes, from satellite observations, from aircraft, from ships, from weather radar, all sorts of different types of observations modelling different variables at different time and space frequencies. But despite having all those observations, we don't have enough information just from the observations to actually solve the problem. It's an ill-posed problem because we're actually interested in all the model variables at every single grid point. So you don't typically have observations nicely arranged so that they lie on the points of a model grid. And there are certain areas of the globe which are particularly poorly observed, tends to be in the developing world. They don't have very many ground stations, there's no weather radar and so on. So we blend together information from a previous model forecast and observations in this assimilation scheme to give us an updated model state. And the way we do that is with an algorithm called 4D VAR. So, as I say, we have observations which I've marked on my picture as red X's, and in these equations below, the equation, the variable Y. And we have and this is kind of a schematic plot against time, and then we have our background or prior forecast, which might look something like this blue line, which in these equations would be the variable xb. And what we're trying to do is kind of find a best fit solution trajectory that fits both the observations and this background field, which is marked in black by this analysis line here, which is our variable x0. And we're trying to find this best fit. So what we do is we minimize a cost function, which is the difference between the analysis that we're aiming for on our background field and the difference between the observations, and a mapping of that background field, a mapping of the field that we're aiming for, which essentially allows for the fact that the observations are not at model grid points and they may not be directly of model variables. So a simple example would be a weather balloon that measures wind speed, which is one of the variables we're looking at, but it happens not to be at grid points, so you would do an interpolation to the model grid. A more complicated example would be a satellite observation which is sitting up above the Earth, and what it measures is the radiance, the spectroscopic radiance off the Earth's surface, which is related to temperature and humidity through a radiative transfer model, which is rather complicated inverse modelling situation. So that H, that H can be rather a complicated nonlinear model. The other terms in these equations, this term here is our background error covariance matrix. So that expresses our uncertainty in our initial first guess background model forecast, and R is our observation error covariance, which expresses our uncertainty in our observations in this observation equation. And the other part of the problem is that it's a dynamical system. It's very important that the final solution that we get is actually going to be a solution of our PDE that is not going to excite all sorts of spurious waves. So we actually solve this problem over a time window indexed by I at the times of observations, and we try to make this subject to the constraint that our solution is a solution of our numerical model of our PDEs. Okay. So it's essentially a non-linear least squares problem constrained by a PDE. So it's quite a complicated problem. So we use a numerical method to solve it. So we're just trying to minimize that cost function. So we do that by basically doing what's called incremental 4D VAR. So it's a looping process. We run our nonlinear model to get an initial, starting from our background first guess. We calculate an innovation, what's called an innovation, which is the difference between the observations and the model equivalent observation. And then we find the minimum of a slightly different cost function, which is essentially, I'm not going to go into the details of that, but it's a linearized version of the previous nonlinear one that I just showed you. So we solve a linear problem rather than a nonlinear problem because it's a lot easier to solve a linear problem using typically an iterative numerical algorithm such as the conjugate gradient method. And once we've found the minimum of the linear problem, that's not necessarily the solution of the full nonlinear problem. So we would actually have to do that outer loop again where we take our linear solution, add it on to the nonlinear problem, run the whole nonlinear model again, and repeatedly solve that. So you solve an outer loop which is a non-linear part, and then solve an inner loop which is a linear part, and do that repeatedly. And so that's the theory. You do it repeatedly till you reach convergence. And there are some theorems. It's a bit like a Gauss-Newton method that you may have heard of in numerical analysis. And you reach convergence, and then that is the solution of the full nonlinear problem, assuming that the problem's not too badly nonlinear. So there are theorems to say that. The problem is that in operations, what happens is they can't actually afford the time numerically to do that outer loop and iterate till full convergence. So they actually just go downhill a little bit and then stop and say, that's all we've got time to do. We've got to run the forecast because a late forecast is a useless forecast. So it's a big problem. The state vector, so that's all the variables in the model that we're interested in initializing for our initial conditions. Depending on the model you're using, that can be a size between 10 to the 7 and 10 to the 9. And you'll have typically about 10 to the 7 observations available. And that's every 6 hours, okay? For a global system. As I say, the time to solve the problem's got 2 constraints. You can't start running it too soon because you've got to wait for the observations to arrive. Okay, so you take an observation, it's actually got to be communicated from the other side of the world to the Met Office in Exeter, for example, before you can actually start running your data assimilation system to run your forecast. So you're constrained when you can begin, but you're also constrained when you have to finish by. Typically, they allow about 40 minutes to run this data assimilation program, and then the actual forecast will only take 15 minutes to run. So you have an hour window to run the numerical model and then get it out to the forecasters, who can then produce a forecast that you can see on the TV, that's used in civil aviation, that's used by the military, that's used by electricity companies, and so on. So, a numerical problem, the speed that you can minimize that cost function is you can actually work out how that's affected what the numerical conditioning of the problem is. So how fast you can expect the thing to converge is dominated by the condition number of the matrix B, which was the matrix, the background error covariance matrix, which is the matrix that models the errors in the prior forecast information. Right, so that's for a current system when you're assuming that the observation error covariance matrix is diagonal, which means that all the observation errors are independent of each other. Now, that's actually a bit of a rubbish assumption, and the rest of the talk is really going to be about what we can do about removing the assumption that that matrix is diagonal. So let's have a think about what observation errors are. So we've got this observation equation. So y are the actual real-world observations that you take with your satellite instrument, for example. And h of x is our mathematical model, which provides us with a model equivalent observation. So it maps from all the model state variables to something that looks like an observation. Okay? And then epsilon is all the errors in that equation. Okay? And we're going to make the assumption that this epsilon is unbiased, so that its mean is 0, and it's got a covariance matrix R. Okay, so it's just a simple statistic. Okay, so what are the sources of error? The main source of error, the first one is instrument noise. So we assume that actually instrument noise is typically uncorrelated, because when you have a typical satellite in the atmosphere, above the atmosphere, orbiting the world, it typically periodically turns round, looks away from the Earth, and goes and looks at a black body to be so that and we know the spectrum for a black body, so it enables it to be recalibrated. So we can make the assumption that noise is uncorrelated, and we'll have some idea what the instrument errors are because that instrument will have been very well tested by the instrument manufacturer. The problem is there are also errors, so those are the errors in the y part of the equation. There are also lots of errors in the h of x, the part that the model that we create. So one problem is that we often use, we're not very good at dealing with water vapour in the atmosphere. So observations that have got clouds in them from a satellite, we typically say, right, we don't want to deal with that, so we're just going to throw them away. Okay, so you have a nice numerical algorithm that says, right, I'm going to go and find all the clouds and chuck them all away as a pre-processing step. But unfortunately, some clouds are a bit too see-through, so we don't always collect everything properly. So we might have a problem from undetected clouds, so it's one of our modelling assumptions has gone wrong. Another type of observation is called an atmospheric motion vector, and that's quite a fun one. Basically, you have geostationary satellites which sit above a particular area of the Earth and orbit with the Earth, and you can, in those images, they might be visible or infrared, so it's just like a photograph, and you can see where the clouds are in a given picture. And what you do is you track a cloud's motion between each different image in time, and that enables you to say what the wind velocity is doing. But you have to assign a height in the atmosphere of that cloud, which is done using previous model information. So you might have an error in that height assignment, which gives you a correlated error. And then there's also a problem called representativity, which is to do with contrasting model and observation resolutions. If you've got an observation that can see some very fine scale detail of something that's going on in the atmosphere, but your model grid is got much larger spacing, it can't actually resolve those kinds of motions. So there's an issue there that will cause errors in that equation. Now the problem with dealing with that is that the magnitude and character of observation errors is largely unknown. You can only estimate it statistically, not directly. And historically, the sorts of observations, when the idea of data assimilation first came along, there weren't that many satellites out there. So most of the effort, and there weren't very many observations, so most of the effort was put into modelling this background error covariance matrix. But now there are a lot more observations, so we have to change our mindsets about where we should put the effort. So typically what we do is we say, well, we're going to have to assume we don't know anything about the error correlations, so we're going to make assumption that nothing is correlated, and we're going to throw away half of our observations to make sure that they're not mutually correlated with each other in space. But these days we're actually moving towards finer and finer resolution modelling to do these high impact weather forecasts for flooding and so on, and we actually need to retain that observed information. So we need to start worrying about treating that R matrix not as the diagonal matrix, but actually treating the full correlations. So this is just an example of a quantity called information content. I'm not going to go into the details of the calculation, but there's the formula if you're interested. Basically, the idea is that this gives you a measure of the amount of information contained in the observations that actually makes it through to the analysis. And if you use, so a higher number for information content means that there's more information, so higher is better. And this is just number of observation points plotted across here. So the blue line here is when you use a fully correlated observation error covariance matrix R, and the red line is when you use a diagonal error covariance matrix R. So you can see that when you use a fully correlated matrix, you retain a lot more information about the field. And the other point to make is that you actually retain a lot more information about the gradients of the field rather than the absolute values of the field. So I won't because time is pressing on, I won't go into the details of the plot. But, so, can we improve those estimates of R? Well, we've been doing some work on errors of representativity, which, if you remember, were to do with differences in scales between what the observations can observe and what you can actually resolve in your numerical model. So here we are, it's just a toy example. This is solutions of the Kurimoto-Shibashinsky equation. And this is a plot against time and the colours, and this is the spatial domain, so it's a 1D nonlinear PDE, and the colours are just the heights of the waves, amplitudes of the waves. So this is sort of a plot of what goes on in time. So one of these plots is higher resolution solution than the other one, or higher smaller grid spacing than the other one. So over to you. Which one is which? Which is the one with the smallest grid spacing? This is the ask the audience question. Can anyone see any? Yeah, was there a hand at the back?
The one on the right.
The one on the right. So why do you say the one on the right?
Looks to be slightly sharper resolution.
Okay. Okay, but well, to me they look like I can't see the difference from the visual, but there are definitely differences between the solutions. You can kind of see these funny ribs in this plot that aren't there in that one, and so on. So, and I think you are in fact correct. So you've got a sharper eyes than I have. So it's actually very difficult to tell in the eyeball norm what the effects of resolution or grid spacing are. So we need some slightly more sophisticated ways of thinking about it. So we've done some experiments using one of the Met Office operational models. And the idea here is just to express this representativity error as the difference between a truth and a modelled observation. And the idea then is to treat a particular very high resolution state as the true state, because we can't actually get hold of the true state in reality. So we're just going to run that model at really, really high grid spacing, high frequency grid spacing, and then treat that as our truth. So we've been looking at temperature and humidity fields, which are very important for modelling, in particular, these high impact weather events. And we looked at a couple of different cases to see if there was a difference in the structure of the errors for different types of weather situations. And the first case, I'm not going to show you both of them, is a cloudy or convective case. So on the left, these are just pictures of what the original fields looked like for the sort of true solution. So this is space for a particular model level. So this is sort of a slice through a particular level of the atmosphere, just above the boundary layer, across the southern UK. And you can kind of see, and the colours represent temperature in Kelvin. So you can see that temperature's got relatively large scale variations. The bottom picture is the same domain but for the humidity field, and that's a log of specific humidity. And you can see that you've got all these little patchy dotty bits which are much more prominent in this than that. And that's where you've got clouds and convection, so sort of summer rainstorms. And on the right, we've got plotted the standard deviations of representativity error. And you can see that temperature field is fairly uniform with height, but there's this great big spike at this level here, which is actually corresponding to where the clouds are. Okay, so the representativity error is going to be the sort of small scale phenomena that are represented by these storm clouds are actually really important. So we concluded after we'd done a bit more work that the errors were correlated, state and time dependent, which is going to make them really difficult to model in practice, unfortunately. They vary with height throughout the atmosphere. They're more significant for humidity than for temperature. And if we use a finer model discretization, they're reduced as we might expect. And they depend only on the distance between the observations, not on the number of observations. So, can we estimate them in practice? Well, there's a technique. This is a typical applied mathematician's approach. Let's try this thing and see if it works, and afterwards we'll go back and see if we can prove that it works. So the idea is that we take, I'm not going to go through the details of it, but let me just flick through. So the idea is we take what's called a background innovation, which is the difference between the observations and the model equivalent observations for that background or prior first guess. And we also take the analysis innovations, which are the difference between the observations y and the model equivalent for the analysis, which is the solution we get from that 4D var least squares minimization cost function. And then if we make various assumptions, which none of which actually hold in practice, and we collect these statistics over a period of time, and we take the average, we can actually do some manipulations based on the Kalman filtering equations that I'm not going through for the sake of time, and we'll end up with an estimate of that matrix R that we're looking for. Okay, so this is a method so what you're doing is you're using the incorrect matrix R in your analysis, getting some statistics out, and then using that to estimate an improved estimate of that R matrix. So in theory, it could be done as an iteration. So an example of the resulting matrix that we get out, so this is for a satellite instrument called ERZ, which is an infrared spectrometer, which essentially measures temperature and humidity. And this is a picture of the matrix that we get out. It's plotted not in the usual way that you'd think of a matrix. This is actually the diagonal of the matrix because we're plotting in a typical plotting way, number of the spectroscopic channels of the satellite from here to here. So you kind of need to think about it shifted the other way. So this is the diagonal of the matrix. You can see it's strongly diagonally dominant, but there's all these correlated blocks, and these big red blocks mostly correspond to surface temperature, emissivity, and water vapour. So those are the errors that we think are actually related to that representativity that we were talking about a few minutes ago. So this is what we did with Laura Stewart, was one of my PhD students. So we did these experiments for the Met Office, and then we got something out, and we thought, oh, well, this looks vaguely plausible. Do we know how good our estimate is? One problem was that we know that this matrix R is a covariance matrix, so it should be a symmetric matrix, but the estimate we're getting out is not even symmetric, so you can do a fiddle and make it symmetric, but do we know how good the estimate really is? Well, we did some experiments in a simple model where we knew what the truth was, and sure enough, we've got a reasonably good result. This is the matrix plotted in a more conventional matrix ordering, and this is just one row of the matrix, and you can see that the diagnosed matrix is the black line, and the matrix that we actually are looking to estimate, the true matrix, is the blue line, and you can see that they basically follow each other up to statistical noise. So that's good, but that's only an experiment, it's not a mathematical proof. We haven't proved it yet. So we did these experiments. The Met Office actually picked up on our work, despite the fact that all the assumptions that are going in are unrealistic. It seemed to produce good results anyway. So they said, oh, that sounds interesting, let's have a go at that. and one of the Met Office staff, Pete Weston, actually tried it out in the operational system. And he found that the minimisation failed to converge. So once he'd done some regularisation of the estimated R matrix, it actually worked very well, and it actually improved the weather forecast over a long period of time when they trialled it. So it's actually something operational in their system, which is a nice thing. You know, you do some research and it's actually benefiting society at large because you're improving the weather forecast for everybody. So that's where we are. I think I just said most of that. So I think, how are we doing on time?
2-3 minutes.
Okay, so I'll skip lightly over some of the rest of this, but the main problems then are this problem with the minimisation. So I mentioned at the beginning that there are some theoretical results on how the 4D var least squares minimisation is affected, the condition number of that minimisation is affected by these two matrices B and R, and we have some theoretical results that say if this R matrix is diagonal, then the conditioning is dominated by the condition number of the B matrix. But clearly, the practical experience at the Met Office is that if you use a correlated R, the minimisation can fail to converge. So there's obviously going to be a problem with the conditioning of R, and that's one of the things we actually would like to look at next, is to look and see if we can extend these results to actually prove some results about the conditioning of the minimisation. So that'll be a mathematical proof that then will have a practical benefit. The other aspect is just the sheer number of computations. When you do the minimisation, you actually have to do matrix vector products between the inverse of this R matrix and a vector. So if this is a large full matrix, that's going to be expensive. So I'll skip over the next bit because we've done some work on looking at computationally efficient approximations. I'll just tell you the conclusions of that experiment. So we considered 3 different approximations to that matrix. One which was diagonal, which is the one that we know loses information, but maybe we can find an optimal diagonal approximation. One where you do an eigen decomposition of the matrix, truncate at a certain level and only use the most dominant eigenvalues and eigenvectors, and what's called a Markov matrix, which has a nice property of having a tridiagonal inverse. And the interesting thing was that if we included some correlations, it didn't really matter what the form of the correlations was, the results we got outperformed the diagonal approximation quite significantly. So even if we have a rather poor idea of what the actual structure of the correlations is, but we put something in, we're actually going to improve the performance. So that's something that's a really nice result, because it means that we can just say, well, we can use a rather poor approximation that behaves well from the point of view of numerical conditioning of the minimisation and numerical computations, and that's going to improve our results because it just gives us an extra degree of freedom to fit the observations in the assimilation. So overall then, we need high resolution observations to provide detail for high resolution numerical weather forecasts. And it's really important that we take account of the correlations in those errors, which hasn't been done until recently, or it's only just being begun to do. And we can actually try and estimate those using output diagnostics, where we make some rather dodgy assumptions, but it still seems to work anyway, so we'd like to investigate that a bit more. But we really need to work harder on computationally efficient approaches to including them in operational forecasting. But the good news is that the inclusion of some correlation seems to produce much better results than not including any, so maybe it doesn't matter precisely what we do. So going forward, we've got a project that was just funded, hooray, to actually begin to work on some of these results and actually really produce some more powerful mathematics and can help us understand the background that can then be used in the operational system. So, thank you.
Only a couple of questions between you and lunch.
Are you essentially running an iterated extended Kalman filter then to produce?
It's very similar to a Kalman filter. It's not quite the same because with the Kalman filter you actually propagate in time the background error covariance matrix, so the matrix that models the errors of the model state. And with this, there's an implicit propagation in 4D-var over the time window that you're doing your assimilation for, but that time window is not. When you stop doing your assimilation, you run your forecast. You actually don't retain that information because it's too big a matrix. It's 10 to the 7 by 10 to the 7, you can't propagate it within the time frame that you've got to do the forecast. The other thing that's not done operationally, at the Met Office, I should say, they don't actually estimate model errors, whereas at some other world weather forecasting centres, there's one in European Centre in Reading, they're very one of the leading centres in the world, the European Centre, actually do estimate model errors. So it's more like an extended Kalman filter in that sense because they're estimating the model errors as well. Yeah.
Any other questions?
I have just, this is related to my project. I have just started my PhD program, so I just wonder, because I'm working on a reduction of traffic accidents in my country. So my question about the data, is it important to work with the real data, or it's if I'm developing a methodology, but it's okay working with simulated data? I guess for traffic accidents, it is said that the type of data is like having over dispersion. So such data, I need the real data to be.
Well, that's an interesting question. I think often with our PhD students, we often don't work with the real data because, for example, the Met Office system is difficult to get in to use the real models and the real data because you need security clearance. So we can't. It's quite difficult if they're non-UK citizens. But the other thing, it's actually really hard to get to grips with the real data, and we tend to find we can actually make quite a lot of progress in understanding what's going on with a simulated system with simulated data, without all the complexities and all the the funny fixes and funny fudges that are going on in the real world system. But on the other hand, if there was an operational person here, they would probably say, well, we don't usually believe any of your results till we've actually tried them in the real system. So I think you have to be quite careful about the assumptions you make in a simplified system. If you're using simulated data, you need to try and simulate what you regard as the important aspects of that data quite carefully.
If I am using simulated.
So if you use simulated data, it's quite important that you understand the assumptions that are going into that. Yeah.
So you think it's not better to work with the real data?
Well, working with the real data is usually a harder problem. So working with the real data is what you aspire to, but possibly if you want to make initial progress and make some if you're trying to test some hypotheses that you want to understand more deeply, then working with a simplified system first. So that's typically what the student that did the work, Laura Stewart, that I've been showing a lot of her results. We worked with simple models first, then she went and did it on the real system, and then we came back, took the results from the real system, and did some more experiments in our simplified system to try and understand them. Is that?
Okay, I think we have to stop here and go to lunch. Just before we thank Sarah again and before you all disappear, I want to say a couple of things, which is that we have discussion groups this afternoon and tomorrow. We will repeat the same discussion groups. We have picked 6 topics that you will see on the sheets out there. Please go.